dominant to recessive or recessive to dominant. Based on that, the priority was set, and based on that, one of the nodes will get hold of the canvas. This one property we have discussed. Another property we have discussed about fault confinement, where we have seen that there is an idea of some state machine type of thing. Different states are defined, and the fault related states of any CAN node was confined to within that state machine. That is the what we can say, the behavior of the possible fault related changes or error related changes that was defined, that was modeled through that fault confinement state machine, and to make the system or the communications predictable. Like fault or error is a very common thing and is possible anytime. But what will happen, how the whole CAN network will handle that error? So that was defined, that was modeled, or to some extent that was made predicted by that fault confinement FSM state machine. Now, this is the one typical feature that we have discussed with the setting of identifier field, with the setting of message ID. We have seen that the bus control is taken by the highest priority node. But this is not the only solution, and we will see here what are the limitations of this solution given in CAN, rather what are some other possibilities. Okay. So before that, just to recap, you remember we have already discussed about that OSI model, where we have discussed and mentioned about this application layer to network layer. But when we are focusing on embedded system, our focus is mostly in this physical and data link layer, where data link layer is mostly related to node communication, and physical layer, in the physical layer we are defining how we are representing the bits, how we are representing the bit, how we are mapping any bits to a signal level or voltage level, everything. Okay. So this is the, just a second, one second. One, sorry, let's continue. Okay. So we're talking about this data link and physical layer. So mostly now we have some idea that how in the data link, a physical layer, when we are talking about some bit level, maybe 1 or 0, how we are mapping them to some signal level. We talked about the voltage differential, where we have seen that CAN high and CAN low voltage levels, and how we are mapping our our idea of 1 or 0 to those particular levels. So that is the main work of this physical level, physical layer. Now coming to this data link layer, one of the main functionality of data link layer is MAC, that is media access control. In CAN, we have seen it is by bit dominance, based on the whoever is having the dominant bit or the recessive bit. Based on that, someone with gain the priority or someone will lose the priority. One thing to mention that when embedded system was first proposed, it was not conceived with the idea that it will connect to the internet. It was, the initial idea was it will be like a closed system. Only few sensors, actuators, their embedded type of communication between them, those things were conceived. That's why we thought that our all functionality or all focus will be will be confined within this two, physical and data link layer. But here, since we are growing, our requirement of connecting embedded system with internet is coming into picture. And at that time, of course, these layers will be effective. Like, we can think about one example. Since we have taken the example of smart cars or automobiles, we have seen the internal embedded communication protocols. But when that smart car is actually connecting to another car, when we are defining today's V2V, vehicular network, vehicular V2V communication, or vehicular to infrastructure communication, of course, at that time you can think about the your CAN-based automobile smart car protocol. You are basically connecting to some internet that may be connecting to another bus network. If it is connecting for V2V communication, vehicle to vehicle, if it is coming it is getting connected over the network to some IoT related sensors, some servers, storages, maybe those are following some ring related network. In case of V2I communication, we can think. So nowadays we are also, since the requirement, since the functionalities, since the features, we have more features we are adding to our embedded system based approaches, the more requirements are coming into picture, and there, of course, we are focusing on these few layers. But at this stage, I will be mainly talking about these data link layer and how the MAC, media access control, is getting handled, and what should be the proper approach in case of embedded system. The reason is that why we are mostly interested in this part, we will see that again, when we are talking about embedded system or embedded design, one important requirement comes into picture, that is the real-time requirement. Whatever task you are doing, you have to finish it within a particular deadline. So remember, everywhere, whatever design approaches, design steps, features we are considering, everywhere we are analyzing whether that real-time requirement is getting satisfied or not, whether I can improve the performance, whether the pipeline or the cache architecture or the any features we are discussing, whether that will help me to improve my performance in such a way that I can meet my deadline or not. And in this case, I have to check the media access control. Whenever multiple nodes are accessing a single medium, whether predictability is maintained there or not. So for that, we have to revisit our existing protocols, MAC related protocols. Probably those who have already gone through some networking courses, they have some idea that what are a few types of protocols we use in medium to check our media access control. Media access control means whenever you are having a shared medium connected with multiple nodes, which of the nodes will get hold of that medium to send or receive messages. So first solution is the first algorithm, the most common approach we discussed, that is KDA sends multiple access. There are two versions, one is collision detection and one is collision avoidance. Now first one, the simplest one, is the collision detection, where we see that any station, any node whoever is connected to the shared medium, shared bus, they detect those stations, those nodes. They are trying to detect what are the activities going on within the bus, within the medium. That is, whether the medium is busy or not. If it is busy, it waits and again goes back to its initial stage where it again listens the activities, and if it is detecting that but there are different types of signals, request transmission signal, clear, if it is receiving clear transmission that it can proceed for the transmission, then it transmits. But it may happen after taking so much care, after taking considering so much, waiting so much to check whether there is any detect activities going on or not. Two nodes may simultaneously check that okay, there is no activity going on in the shared medium, so let's transmit. If that happens, that means after the transmission, any of the node may detect the collision. Okay, if that happens, that node will stop, it will transmit some jamming signal, and then it will again go back to its initial state to listen the activity. If there is no collision, of course, it will go to the complete its transmission. So this is the basic idea of carrier sensing. Carrier means you are sensing the medium. One improvement to this is carrier sense multiple access, where multiple nodes are checking the carrier, checking the shared bus, and it is also trying to do the collision avoidance. What will happen? In this case, initially they will again think, okay, it will again start to sense the carrier. If the carrier is idle, there is no activity going on, then it will again wait for some interframe gap. Why it is important? To give some time whether to check that if some other node has already transmitted and the information has not been reached to that particular node. So after this interframe gap, it will transmit the frame. If some collision is getting detected, that node will send some jamming signal, increment the collision number, and there is some limit, of course, that it will check whether the limit is reached or not. Otherwise it will try over and over. If yes, it will abort. If it is no, that means limit of its trying has not reached to the maximum threshold, it will select a random number in a particular range. Now we will again come back in case of an embedded scenario. We will come back to this part because this is very critical if we are choosing this algorithm in your embedded scenario. Now what we are doing in the general CSMA, you are selecting a random number within a particular range. If that random number is k, then it is setting a particular back of time, maybe waiting time you can consider. That waiting time, maybe if the chosen random number is k, then it is waiting that k into x time slot, and then it is again sensing the carrier and the loop is going on. So that means compared to the previous one, where if you go back, you are just detecting the activity and then transmission is taking place. Here, more precautions has been taken and this part is more formal. So of course, you can understand in normal scenario, this CSMA is more, acceptable compared to CSMA CD, collision only detection. You are in this protocol, in this algorithm, you are not only trying to detect the collision, you are also trying to avoid the collision. Okay. So we will again come back. We will first explore what are the possibilities quickly, and then we will see what can be the suitable solution. The next solution is the polling. Polling means where there is a single master node who is checking who is polling basically with some proper polling signals, that if all the other connected nodes, they're interested to send the message. But this polling technique is not very useful in embedded system. The reason is that it is heavily dependent on the single master. So if there is any reliability issue, if there is any failure in this single master, then your overall message transmission in your overall network, your overall communication will not be go through properly. So that's why we do not focus much in this polling technique in embedded scenario. Next one important important protocol in case of embedded scenario is this token passing, where stations are connected like this in a ring manner. Your nodes are connected in this ring manner, and one token is selected and one start station has been selected. Start node has been selected. This station or node is holding the token, completing its message transfer and releasing the token to the next station. And this way, this token is moving from one node to another. So you can understand from this diagram, this token passing is useful if you have chosen your nodes to be communicated in a particular ring manner. Otherwise, in other types of arrangements, if you are trying to handle this token, that is not very useful. I mean, that is not very easy to handle tokens in some other architecture form of how you are placing your nodes. For example, when we have talked about CAN was like this. That was bus architecture, right? You have a central bus and your nodes were connected like this. So in this case, the token passing was not very useful. So the next one is the bit dominance that we have already discussed. We have seen that here, based on which bit is making a translation from dominant level to recessive level, or recessive level to dominant level, the priority is confirmed. So you need a message ID, particular message ID, and based on that message ID, your dominance over the bus level, your dominance is expected or is established. Okay. So this bit dominance type of protocol we heavily use in CAN scenario. Another approach is TDMA, that is time division multiplexing. I think in various ways, some way or other, you have the idea of this time division multiple access, where you are actually dividing your communications in different time frames, and smaller slots are allocated to multiple sources, different sources. So when the slots of this particular source, maybe for this source A, in this particular slot, this particular source A, will completely get hold of this communication channel. So that is based on the time division, you are allocating some slot to your sources. So these are the few approaches that we have in our carrier sensing or carrier multiple access. In case of multiple access scenario, how will you assign your carrier to some particular node? So what are the algorithms? Again, if we go back, carrier collision sensing and collision detection. Here we have added extra feature in collision avoidance. So of course, this collision avoidance, you can understand superior than that simple collision detection. Then the polling, which as we mentioned, that polling is not very much suitable when we are talking about embedded scenario. Token parsing, it may be useful when you are arranging your station, your nodes in a particular form. There, this token parsing is possible. Bit dominance, of course, this dominance is there established in some particular particular protocols like CAN, but there you need added features from your signal level underlying hardware support. You need to have to implement these type of bit dominance. And next one is the time division multiple access. Now the question is, since you know the features, the requirements of embedded systems, which of these carriers, MAC protocol, you think will be suitable when you are talking about embedded scenario? Because in embedded scenario, there are two things. One part is there are very straightforward operations. Those are routine operations. So when we are having these routine operations, we know how much time we need to allocate for a particular source so that they can finish that routine operation, or after which time we can actually preempt, stop that operation, and then we can allocate the resources to some other source. Then again we can come back, and then if we allocate the source to this source A, then what will be the total number of slots will be required to finish the whole task. So those tasks, the required times for those tasks, for this routine task, those are very known. So in such cases, of course, time division multiple access is very good because everything is predictable and implementing this TDMA is very much simple. You do not need an extra support, underlying support, like you need the spatial implementation features like you need in bit dominance technique. So wherever we are having this routine type of work, there this TDMA feature is very useful. But when you are having sporadic, like event-based features, think in that case. Here for your frame, for every time frame, you have divided smaller slots to every source. Now it may happen if you are considering all the routine tasks from this source A, source B and source C, this is fine. The slots will be filled and you can use those timing slots. But on the contrary, if it happens that those sources are event driven, the tasks they are generating, the slots they are using, they will be completely event driven. In that case, it may happen in this frame, maybe you have specified some slot for this B3, but this task that is not happening most of the time, these slots actually it is going idle. It would have been better, of course, now you understand, if you can assign that slot to some other sources so that they can finish their routine task earlier. So you can gain some amount of, gain something in terms of your performance, general performance of those routine tasks. So that way, in spite of the fact that for routine tasks, this TDMA is very good. For sporadic tasks, for event tasks, this TDMA is not so much meaningful. So what is our option? Of course, bit dominance, we have seen that we have to think about some extra hardware level, some special support, so implementation support. So that is not very good. Not always you can give that support. Token parsing, for that you have to exactly maintain this type of ring structure. That is not also always good, always not possible. Polling is not a solution. So we are coming back to our discussion to this CSMA. Okay. Of course, whenever, if we again go back and think, whenever the event is there is some event coming from a particular source, maybe in the source B, it can sense the carrier. it can sense the carrier, check whether the carrier is idle or not, and then it can again after interframe gap, it can transmit the frame. Again, if there is a collision detection, it can wait for this random number time of slot, and this cycle can go through. So of course, since there is no pre-allocated slot like we have used in TDMA, there is no concept like that in CSMA. Whenever requirement, the node can sense the carrier and they can wait or they can send the frame. So this way, you can of course understand for event-driven scenario, this is a proper choice. There is no loss, no harm. But there is one difficulty. Can you identify what is the difficulty? Anyone? Are you there? First tell me, is there any problem? Whatever we have discussed so far? Hello? Are you there? Everybody?
Yes, ma'am.
Okay. Any part? Is there any doubt? Or can you identify what is the problem when we are trying to choose? I mean, when we are deciding, okay, considering all the other options I have, the CSMA CA is the best option in Mac control in embedded system. The problem is here. Remember the algorithm. The algorithm says if there is a detection of collision, then you are sending the jamming signal, you are incrementing the collision number, everything is fine. But after that, you have to select a number, random number, and you are waiting back of time, that is the k into x time slot. Now this k is random. That means total time slot, number of time slots that you are waiting, that is also random. That makes these part not so deterministic. How much time you are actually waiting to go and try again to send your message, that is not very deterministic. But if you think about our real-time requirement, first requirement is it should be very predictive. Whatever task you are choosing, whatever features you are choosing, there must be some prediction so that you can actually analyze. You can, whenever you are analyzing how much time it is required to finish your task, there should not be any ambiguity. Otherwise, you cannot never actually estimate what will be your finishing time of your task. And you cannot never check whether your task is actually getting finished or not within the deadline or not. So in that way, this is the main problem. In spite of the fact this is the base choice in case of embedded Mac solution, but this is the problem where whenever you are choosing the time slot, you are basically selecting a random number within a choice, within a given range. So whenever we have to think about Mac control, Mac solution, media access solution, what we consider whenever we estimate the timing requirement. Okay, what is the total timing requirement? There we consider everything, right? We consider the timing requirement for our software execution, also the timing execution of sending and receiving the messages, the intercommunication between the nodes. Now for that intercommunication, when we do this worst case timing analysis, we consider, since see, this is a select a random number in the range. Okay. So that time we do, that's why whenever we do analysis, timing analysis, you will always see that the term we use, that is worst case execution time analysis, WCET. Because in such, for these such features, here we consider that what is the worst case timing requirement possible. What is the worst case number these algorithm may choose? That means how much higher than these k may be. Because higher the k into x will be higher. So whenever you will be waiting for that higher number of time slots, your waiting time for the next try of your sending message will be high. And that will actually directly impact on your timing requirement of your next level processing. So this is the whole thing. Not only whenever you are designing a software, it is not only the whole thing. Not only the thing that what instructions you are choosing, what processors you have chosen, whether that processor is giving the backward parallelization or those type of supports or not. Number two, whether that processor is giving what type of memory architecture it is using. Number three, when you are going for some node-to-node communication through some shared media, what algorithm you are choosing, everything will affect the timing requirement of your overall execution. And that is the main thing. Whenever you are designing in software in embedded domain, that timing and analysis is the most important part, because that is the most important thing that will affect, that will determine that whether you can go in this way or not. So this way, this is the feature what we consider when we come to this what is it, the data link layer and for shared media. Okay, this is about MAC handling or media access control. So is there any question in this part? Then I will talk a bit about the error handling. But first I have to know, is there any question? Anybody? Okay. No questions. Okay. Then I assume that at least you have got some idea. So this is a real-time feature that you understand that protocols themselves are not strictly event or state-based. So whenever we are thinking about embedded scenario, we have to merge different features, both how we are handling the event-driven scenario and some time division, some state-based scenario. And we will see, I mean, not in this course, actually there are different other protocols, maybe we are not discussing here. There is another protocol I should mention, that is FlexWare protocol. If you just go and search, you see how FlexWare works, you will see there are two types of segments in the FlexWare, where in one segment you handle your general purpose task or very routine task. I should not say general purpose task. And there is another segment that is called dynamic segment. In that dynamic segment, you handle the event-driven task. In that way, you give priority to both of your types of tasks. You you maintain the predictability of your routine tasks, that you ensure that they will finish in time. And also through that dynamic segment, whenever the event-driven processing is required, event-driven request handling are required, and that part also ensured. So that way, the more advanced protocols, modern protocols, they try to actually incorporate both the features so that they can handle in a better way state as well as event-driven situations. More efficiently. But that feature, I think you can understand as of now, that basic CAN, whatever we have discussed, that is not there. So there are different versions of CAN-FD and all. We don't discuss it here, maybe in another class. So now this is one feature that we have discussed, how media access control. In that part, we are trying to incorporating determinism. The second one is you have done everything. You have chosen your communication properly. You have ensured predictability that, okay, with your software execution, controller execution, and your communication, everything is finishing in time. That means you are meeting your real-time requirement. But what happens if whatever you are delivering, whatever communication is going on, that is error prone? That means whenever communication is coming into picture, two important features you have to ensure. One is error handling. If some error occurs in your system, or the security, whether there is any information leakage, whatever communication is taking place. So security is beyond the scope of this, this fundamental course. But about error detection, you will see these are different types of, if you note down, different types of error possible when you are considering some embedded scenario. Among them, we will uh, we will not be discussing all, because if you consider this tail message or some repeated message, they can be handled if you add some timestamp or some serial number type of features with your message. Like, you remember when we have talked about how we are adding, forming our message frame. There we have added some message, we have added some start, stop bits, we have added some acknowledgement signals, we have added some error related CRC field that I mentioned that I will discuss later. So with that, if you add some field like timestamp, these type of errors can be handled. Now this station run-on, failure propagation, these things, and these intermittent errors or this hardware errors, cable breaks, they are hardware related issues. So for that, you have to keep some backup circuit or hardware support, those things you have to. But here we will mostly discuss what modification we can do in our message frame. What additional information we can put in our message frame so that with that information, our sender can detect whether the communicated value, based on that information, the receiver, whoever receiving the data or the data stream, they can understand, okay, whatever I have received, that is error free, or some error has been incorporated during the course of transmission and I have to reject or discard it. For that, so different types of errors you can go through, but we will be mostly discussing three types of errors. That is, this is a three error detection techniques. This is only for whatever based on information we are incorporating in our message frame other than time frame or counter related informations. So one is single parity check, another is cyclic redundancy check, another is checksum. What does it mean? Simply, parity means, maybe we have already talked about it. Maybe sender is sending some data, it is computing the parity. It may be even parity or odd parity, but anyway, it is checking how many numbers of one are there. Based on that, it is setting 1 or 0. If it is even parity, or here maybe it is odd parity, and that way. Then it is sending to the transmission media. Then in the receiver side, whatever data stream receiver is receiving, whatever frame it is receiving, it is again computing the parity and checking whether it is matching or not. If yes, it is accepting the data. If no, it is rejecting the data. Okay. So based on that, this is the idea of parity which helps. That means you are adding a single bit, parity bit, that is detecting the error in your design, detecting the possibility of error, and change of mismatch of these particular single value will give some idea to the receiver. Okay, there is some possible error incorporated in this data stream, right? But this error detection technique itself is very limited. The reason is that, see, this is based on only single bit. Okay, it may happen that whenever due course of transmission, you are only considering that one bit if changes, then this parity process can detect that change. But what happens if two bits changes simultaneously? Let's say 0, 1, one pair is changing to 1, 0. Then effectively, actually your CM data, maybe this 0, 1, it is changing to 1, 0. In that case, your total number of ones, total number of, total effective parity will be same. But due to the change in multiple bits, receiver will not understand that there is some change. There is a modification in the actual data, whatever sent from the center. So that is a limitation of this single parity check. That's why we need some added, improved error detection technique that is called cyclic redundancy check. Okay. In the cyclic redundancy check, see what we do. This is our data word. We extend them based on some bits, and then I will actually give you one. Share with you one example so that you will understand how to set this number of bits. Okay. Then you have decided one CRC polynomial. From their bits, you are dividing and you are adding this remainder with your actual data word. Okay. Now this is getting transmitted, and the same way there will be again the division, and there is a CRC checker in the receiver side that will check whether whatever bits you have received and whatever bits from the calculation in the receiver side based on these values it is coming, whether they are same or not, expected values and whatever values received, they are same or not. If it is same, you will accept that, otherwise you will discard that. So what is the basic difference between the previous one and this one? In bit parity checking, we are just considering one bit, a single bit and bit level modification. Of course, the advantage is that you have to add only a single bit or size of the information. For this error detection, you are adding in your message frame. It is very small. It is actually small. I should not say very small. It is small compared to your CRC checker. Because in CRC checker, you can see what is the number of bits you have to add. That will be also dependent on the size of this polynomial or the divisor. So the main idea is, in case of embedded scenario, you have to choose what is the possibility. How much your medium is noise prone. If you want more error detection, more support to this error detection, then you can add these type of CRC, complex CRC checkers. For that you have to support more number of bits. But when again in embedded scenario we are considering real-time requirement, each of your message frames, the size of your message frames, due to the choice of the CRC or parity bit type of algorithm, whatever way you are going, based on that, the size of your message frame is actually varying. If you are using parity bit, of course, the size is expected to be lesser of your message frame. That means you are sending the same message, but overall communication bits are increasing in case of CRC. In that way, you can understand in terms of bit size requirement, of course, this parity checker is more effective in embedded scenario where you have everything restricted. You have your restriction in time, restriction in resources, restriction in bandwidth. At that time, this parity checker may be effective. But if you are actually thinking in terms of error detection capability or stronger error detection possibility, in that case, of course, you can understand CRC is a better choice. So that means that again, based on your requirement, whenever you are actually trying to choose any error detection scheme, then also you have to analyze that what type of error detection scheme. First of all, what is your requirement? Is your medium is really very noise prone? Then you have to, of course, support some serious checkers, serious error detection schemes. But if it is very less noise prone and you are really having some constraints in terms of your bandwidth, bit size requirements, in that way, this parity bit checker may be a better choice in case of embedded scenario. So these are different hardware related techniques. You can check it. That is, in most of the cases, you are basically supporting some added circuits. I'm not discussing. Third one, another support, it is required in case of checksum, DMA and checksum. I'm not sure whether you know about DMA or not. DMA means direct memory access. Direct memory access. So what is the main idea here? Why it is important? See, in embedded scenario, again, as we discussed we mentioned repetitively that timing is a very important issue. So when you are actually executing few sets of instructions, that time your processor is busy, your memory is also busy, right? Your processor is fetching data from the memory and it is performing that execution. Okay, for that you have the data buses, for that you have some latches, everything is busy there. Now you think, according to this is a very common scenario in embedded systems, that is sensor driven. Maybe your sensor is generating some data, you are and that data need to be uploaded to the memory. Maybe that will be used in some subsequent instructions by the processor. Or your memory is generating, your processor is generating some data that to be supplied to some other peripheral. So in this case, this read and write operation is nothing related to your processor, because here the only necessity is whatever value your sensor has generated, you have to store that to the memory, or whatever value you are having, you have already stored in some segment of your memory, that part you have to take back to some peripheral, you have to supply to some peripheral device. Okay. So in any case, we know whenever we do some processing, whenever we send some request, we say that processing goes to that processor. That means ideally the idea is whenever that sensor is generating some data to be stored to the memory, it will send a request to microprocessor or your processor, any processor you are using, not this microprocessor. And that microprocessor will analyze that request and it will send and store the data to this memory part. This is the general idea. Okay. On the other way around also, whenever some peripheral is requesting to read data from the memory, it will send the request to your processor and the processor will send the instruction to memory and it will fetch the data to the peripheral. But if you are going through this, through this traditional way, I should say, then every time just for simple read or write of data, your processor is you're making your processor busy. That means it is that instruction cycles or that machine cycles, your processor, if that simple read write request you can cater in some other way, your processor can actually get involved in some meaningful control instructions. It can actually execute in some meaningful control instructions. So DMA, this is an added controller, is that support to your processor. So you can see in this way, here are direct connections possible to your DMA controllers. DMA controller means direct memory access. So whenever this type of peripheral data read or write request is there, DMA sends a request to the your main processor to get the control. And once that control is acknowledged, the data transfer directly takes place from this peripheral to this memory. Okay, that means DMA is just fetching that value from your sensor and storing in the memory, or from memory, DMA is fetching some memory segment values and providing that support, redirecting that to some peripherals. So memory microprocessor is not, your processor is not getting involved in this transaction. The advantage is that microprocessor or processor is free at the time and it can execute any other instructions. So this is the main idea of direct memory access. If you are not familiar with these terms, you just go to that Peter Marvedal book. There is everything. This part is also there. So you can go through the idea of DMA. Okay. So what we are talking about, the error detection in such cases, you can see in these cases, whenever you are just doing some memory read or write, it is not important. You understand that this is within a particular closed loop system. It is not exposed to network. It is not going through some noisy channels. So you have the idea. It is important to note that whether that it is not important that to check whether some bit has been modified or not, because you know that the channel is not so noisy. Only you have to check that whether whatever number of transmission request has been sent from this peripheral through this DMA controller, it is going to this memory or not, or the number of bits is same of whatever requested or not. That is received, or whatever same that is received or not. So in that case, checksum is a value that supports, that gives the idea whether that ensures whether that number of bits in the transmission message is proper. Okay. So how it does, just to give you an idea, checksum values is generated based on some crypto hash functions. Hash function means you can directly think about that this is one-way function. When in one-way function, it is having a property of collision resistance. That means if two messages M1 and M2, you are passing to that hash, to this hash algorithm, it is very difficult. Actually, difficult means it is a very hard problem to find hash values of, if hash M is equal to hash M1 is equal to hash M2, to occur this situation, this is very difficult to have these two values same. So this is the collision resistance property of hash functions, and with that hash values, if you are creating this checksum values, that means whatever number of bits you are transmitting, based on that you have created some checksum value and you have added. Then in your receiver side, it is getting checked whether that hash value, it is also receiving some number of bits, and it is that hash algorithm is known to the receiver side also, and the receiver is creating that particular same checksum value. The same idea whatever we have discussed in priority or CRC. Just here we are using the checksum to check not exactly the value, but here the number of bits. And both the sender or receiver is getting the idea, okay, the whatever value number of bits has been transmitted, that is received. So these are few ideas about how, what are the suitable strategies of choosing error detection algorithms in embedded communication. And we have also discussed that what are the suitable MAC algorithms, or what will be our strategy to choose MAC media access control algorithms when we are in embedded scenario. Okay, so here are a few references. In this reference, you can go through this part. It is written a very nice way. Just two things I want to mention that someone asked me about, because mostly this is my last class with you. Next week we will have a written exam. Other than that, maybe from tomorrow onwards, Professor Shorkar will be taking your class. Okay. So if you have any questions, you can mail me, you can ask me. We will maybe take one extra class, maybe in the extra slot, and we can discuss and solve your doubts, whatever you have. Just go through the subjects, go through the topics, and let me know if you have any doubts. This is just 2 slides. Someone asked about the bit reverse addressing. I didn't get the time to discuss about that. Just to give you the idea, we remember that bit reverse addressing we mentioned in FFT scenario in DSP processes. In DSP processes, mostly handle these type of FFT algorithms where they need these type of inputs. This X0, then X2, then X4, then X6. In this way, the inputs should be given for next level processing. For this reason, you remember, when we discussed about cache, if you are going for general addressing, right? If you are storing 0, 1, 2, 3 in the sequence, there is a possibility that this 0, 1, 2, 3 is actually filling one of your cache block, not 0, 2, 4, 6. So that's why this reverse addressing we use. Where you can see, if you see this left side and if you see this right side, if you reverse these blocks, and then you will get the sequence of this bit reversal. Like if you are arranging the binary output of 0, 0, 1, 2, 1, 0, 1, 2, 3 and all, and if you reverse the LSB and MSB, you will get this bit reversal sequence. So whenever the addressing is used in DSP processors, they use these bit reversing sequence to store these type of values in a single cache block, or to maintain the special locality. That is, whenever you are actually hitting one cache, with that you can actually gain maximum. You can fetch maximum consecutive required values. So for this reason, these type of bit reverse addressing they use. The second one, someone asked about this USB 3. I have already shared one document that our drive, that is for the whatever specifications. There are different modes used, USB 3, some power handling techniques, some memory features. For that reason, that is the main reason why you can gain in terms of that you can gain the improvement over USB 2 and other previous features. Okay, so if someone is interested, you can go through that drive link and you will get the information. Okay, so this is all about a very brief idea about embedded communication and that modern techniques. If you today, I think time is over. So if you have any question, whatever questions you have, you can, if you have time, you can ask me now. Otherwise, you can send me mail and I will answer, and maybe we can take an extra slot if you have more and more doubts. Okay.
Excuse me, ma'am.
Yes, tell me.
Ma'am, so we'll have the class test next week, right?
Next Friday. Okay. Whatever I have taught, based on that, you have written class test. Maybe 1 hour class test on the next Friday. Okay.
Okay, thank you, ma'am.
Okay. Or maybe some other time. I will fix that. Okay.
Okay, ma'am. Thank you.
Thank you.
Thank you.
Thank you. If you have any questions, just mail me and maybe we can discuss. Thank you.